The first bond you learn about are standard 2-center 2-electron bonds. This is the type of bond in H2, water, and methane where 2 electrons are shared by 2 atoms. These are the meat and potatoes of bonding that are everywhere, holding much of chemistry together. However, there are more exotic bonds out there that are sometimes important. The escargot or caviar of bonding. Some eschew these exotic bonds, turning up their nose at the finer things in life. On this channel, we do not. We embrace the exotic sides of chemistry, so here is the first of these more exotic fare, the 3-center 4-electron bond, sometimes called the omega bond. Let's take PCl3, which is an electron-precise, normal valent molecule, and compare it to PCl5, which appears to be hypervalent. Valency is somewhat of a misunderstood term at times, but it literally just means the number of bonds to an atom. Hypervalent means it has extra bonds from what you would expect, and we expect phosphorus and other group 15 atoms to form 3 bonds. For the neutral atom anyway, like nitrogen and ammonia. If PCl5 has all 2-center 2-electron bonds, it has 10 electrons around the phosphorus atom, 2 for each bond. This is a violation of the 8-electron rule you learned in general chemistry or maybe even in high school. People wondered why PCl5 was a stable molecule because of this rule violation. PCl5 is a colorless or often slightly yellow solid. There's evidence that at high concentrations and in the pure compound that the chloride ion may be transferred from one PCl5 to another to make a cation-anion pair, PCl4 plus, PCl6 minus. Other metastable forms have been identified as well. At low concentrations, it can just be neutral PCl5. How does phosphorus form 5 or even 6 bonds like this in violation of the 8-electron rule? Put another way, what do the lines mean when we draw PCl5 like this? At one point, it was thought that phosphorus could perhaps employ higher energy d orbitals in bonding. Perhaps you've even heard people espouse this theory. Folks working in the main group chemistry soundly rejected this theory in about the 1980s and earlier. The d orbitals are too diffuse and too high in energy to be involved. Instead, it's believed that the 8-electron rule is always followed. No stable main group compounds have atoms exceeding 8 electrons on the atom. Instead, it is the 2-center 2-electron bond that is sometimes replaced. So what is the 3-center 4-electron bond? Let's describe it using both MO theory and hybridization theory. The simplest compound with a 3-center 4-electron bond is perhaps xenon difluoride, which is a linear molecule, so let's use that as our example. Here's the Lewis dot structure. While we're going to do the MO theory explanation, let's borrow a principle from hybridization theory to start off because it will make things a little easier. Namely, Bent's rule, which we have a video on that is linked in the show notes. It says that the bond to a more electronegative atom will have more p character. Every atom in xenon difluoride has 3 lone pairs, which can be thought of as bonds to a group with 0 electronegativity, which will use as much s character as possible. We will assume the bonds between xenon and fluorine are being made with pure p orbitals, which turns out to be an excellent assumption. Because there are 3 lone pairs on each atom, which will use up 3 of the 4 possible hybrids, that leaves us 1 pure p orbital on each atom to form our MOs. We'll end up with 3 MOs from 3 p orbitals, 1 on each atom. There will be a fully bonding MO where there are n-phase interactions between the xenon p orbital and the orbitals of both fluorines. Then there will be a non-bonding MO where the xenon's pure p orbital doesn't have the right symmetry to interact with the salx of the fluorines. Finally, at highest energy will be a fully antibonding MO. Into these MOs, we need to place 4 electrons. 2 can go into a bonding orbital, and 2 will go into the next highest energy non-bonding orbital. This gives 1 bonding interaction to localize across the 2 xenon-fluorine interactions. In other words, the bond order between each xenon-fluorine is 1/2. The hybridization theory picture of the bonding is quite simple. You can have a full xenon-fluorine bond to one side of the xenon cation and fluorine anion, then you can do the same to the other side. Still here, the bond order is 1/2 to each fluorine. Are the bonds in xenon difluoride really just half bonds? It seems so from the data. Let's compare with the closest normal valent equivalent, which is iodine fluoride. Iodine is right next to xenon, and the IF bond should have a bond order of 1. The IF bond is significantly shorter at 1.93 angstroms compared to the xenon-fluorine bonds in xenon difluoride at 2.14 angstroms, suggesting a higher bond order in IF. In addition, the xenon-fluorine bond energy is 32 kcals per mole, almost exactly half that of IF at 60 kcals per mole. These 3-center 4-electron omega bonds in the main group always use a pure p orbital and have groups that are 180 degrees apart, like in xenon difluoride. If your compound is hypervalent because it has too many single bonds, you should look for a 3-center 4-electron bond to understand its electronic structure. Let's return to PCl5. An omega bond is more often found with other types of bonds, especially good old 2-center 2-electron bonds. The structure looks like a trigonal bipyramidal compound with 5 bonds, and 2 of those bonds are 180 degrees apart. We can think about this bond on the axis as being an omega bond. If it's an omega bond, then we would like to think these 2 resonance forms would be the major contributors. Look at what happens. The phosphorus goes to an 8-electron species, a phosphonium. The bonds to the equatorial chlorines would just be 2-center 2-electron bonds, so they can have a bond order of 1. In fact, the phosphorus can use sp2 hybrids 120 degrees apart to form these bonds in the equatorial region, just like carbon and graphite. The bond order of the PCl axial bonds would be lower than 1, and if only these 2 resonance forms contribute, it would be 1/2. One of the things that we would expect is that the axial distances would be longer because of the lower bond order, and there's a structure of the compound from electron diffraction. The equatorial PCl with a bond order of about 1 has distances of 2.020 angstroms, while the axial distances were much longer, as expected, at 2.124 angstroms, consistent with our picture. Let's look at one last example, an interesting compound found all over YouTube, like in this short video from a Mythbusters that shows an aluminum foil boat that floats on the heavy gas, SF6. There's a short on YouTube of Adam Savage inhaling SF6, which makes your voice very deep. SF6, or sulfur hexafluoride, is another hypervalent compound with too many single bonds, so it uses omega bonds. SF6 is octahedral, so all of the bonds are 90 and 180 degrees apart. If we want to make 2-center 2-electron bonds 180 degrees apart, we can use sp hybrids, so we can make 2 strong 2-electron bonds this way. Then there are 2 pure p orbitals on the sulfur left to bond with 4 fluorines. It can do that by making 2 omega bonds. So we can get hybrids that look like this with 2 2-center 2-electron bonds and then 2 omega bonds. There are lots of resonance forms making all the bonds identical. There you have omega bonds, one of the more exotic types of bonds that are actually fairly common in inorganic compounds. So keep an eye out for this bonding type wherever you see hypervalency. Thanks for watching. We make these videos for fun and to give back to the community. Please subscribe, give us a thumbs up, and take a look at the rest of our playlist, which has videos at a variety of levels. Hit notifications so you don't miss anything because we drop vids only occasionally. Thanks.